Hello and welcome to the STEIL Galton board tutorial. In this video, I will cover the mechanics and uses of the STEIL Galton board model for understanding normal distributions. The model was designed in order to allow students who are blind or visually impaired to be able to observe the way that a normal distribution, or bell curve, can be generated based on the probability of where objects falling through a network of branching paths will land. It is composed of two printed components, the board housing and a snap-on cover, as well as a set of 200 airsoft BBs that will act as random objects. The airsoft BBs were chosen for this model because of their uniform shape and relatively cheap cost. The cover snaps onto the top of the board housing using two fitted plus shaped holes corresponding to the same shaped tabs from the main board housing. The cover has a smooth side and a side with a set of points sticking out. These points, or rod protrusions, correspond to an identical set of protrusions in one of the chambers of the main housing piece. So the cover should be attached with the protrusions pointing inward and the smooth surface pointing outward. The housing part consists of three sections. The first section is an empty chamber where the BBs will be placed initially. They will drop into a gap at the bottom of the chamber when the Galton board is set upright. All of the BBs will eventually fall through due to the sloped shape of the walls leading down to the gap. The gap then leads to the second section, which contains a chamber filled with equally distributed rod protrusions that block passage of the BBs as they fall, knocking them left and right at random. Once the BBs make it through the randomizing chamber, they will then fall into the third section of the board. This third section contains separated columns that the BBs will fall into at random. If set up correctly, a rough bell curve or normal distribution will be generated. Students can feel the height of each column to identify the rough shape of the bell curve because the BBs stick out from the column by a small amount. It is important to explain to the students that only about half of the beads in any column will be sticking out to be felt, and that pushing into the column will press the beads backward and upward. The board was designed this way intentionally to increase the accuracy of the bell curve. The model works best when it is turned upright slowly while being held from the sides. Pressing on the top and bottom of the case will apply additional pressure to the BBs inside, causing them to occasionally get stuck and not fall through the gap from the first chamber or get stuck in the randomizer chamber. To reverse the process, the board simply needs to be inverted and shaken back and forth until all of the BBs have made their way back into the first section chamber. This does take some patience, so shake well. Thanks for watching the STEIL Galton board model tutorial. We hope this model will be helpful for exploring probability and normal distributions. As always, a link to the model's STL files is in the video description.